Hi, my name is Alan Phipps. I lead the MCU compiler team for Texas Instruments in Houston, Texas. And I'm going to talk really quick how you can use source-based code coverage in an embedded system and some of the challenges. So code coverage is the measurement for how thoroughly your code has been executed during testing. And this is very important in embedded applications. It's a requirement, in fact, in industrial and automotive markets for functional safety. You want to ensure that you have tests that test all of your code that you've added. The last thing you want is for a customer to discover some lurking bug that's actually in a piece of unexecuted code that you didn't actually fully test. Code coverage helps you ensure against this. LLVM's code coverage capability will provide some useful reporting for you, including a source level view, as well as a summary coverage report with all of the coverage criteria outlined for you, including branch coverage, which is something that Texas Instruments has added, and we're in the process of upstreaming right now. The problem, though, is that embedded devices have very tight memory requirements, and LLVM's code coverage capability has large size requirements. It's going to add instructions on top of your application to instrument counters so that it can track the various execution paths in your program. It's also going to bring in a lot of runtime control code for profile data merging, and there's going to be additional data sections too for the counters themselves as well as other coverage data. There are some things we can do to reduce the size thanks to the flexibility of LLVM, and these are a few of the things that we've discovered at Texas Instruments. The first thing you can do is ask the question, do all code coverage data sections really need to be in memory? No, they really don't. Code coverage relies on several data sections. Out of all of these sections, the only one that really needs to be in memory is the one associated with your profile counters, because that's the one that's actually touched at runtime when you increment the counters as the execution proceeds. The other sections can account for between 80 and 90% of the actual coverage data, but don't require runtime modification. You could move those sections out of memory and just preserve them in the object file. And if you do this, you can extend the LLVM prof data utility to accept an object file argument. So this would allow you to move all of the processing of data, all of the downloaded profile counters and profile counter merging offline. Now, if you've moved all of that offline, you can also look at how you can reduce the runtime support that you actually need. In fact, there are many runtime features included that are unnecessary for embedded platforms. Klang's profile library clocks in at about 100K for ARMv7m, which is quite large. You can remove all of these features and just reduce the size of the library down to what you need to write the counters out from memory. And you can reduce this significantly to about 4K, which is an incredible size reduction. Now, an obvious drawback to doing this is that you lose some of this runtime capability, like profile-guided optimization and being able to read profile data in during runtime. But on an embedded platform, when you're mainly just interested in code coverage, you really don't need that capability. Another thing you can explore doing is reducing the size of the counters themselves. Currently, they're set at 64 bits, but in embedded applications, you can get away with smaller counter sizes. Even a reduction to 32 bits would be a 50% obvious reduction in size. You could go even further and make the size configurable to any reasonable size that suits your embedded application, like 16 bits or even 8 bits. Now, an obvious drawback here is that the smaller your counter size, the more vulnerable your counters are to overflow during execution. But instead of using a standard addition to increment your counters, you could use a saturating addition operation instead and prevent against that. You still won't have the accuracy of the counters if you do reach that limit, but at the very least, you'll be able to tell that the code path was covered. Adjusting the counter size is not something we've done yet at Texas Instruments, but it's something that we're looking at exploring. All of the other items we're planning to upstream at some point in the future, but these are all configurable and you can do them today if you'd like. So I hope that was helpful. Thank you very much.